by far the biggest offender in terms of injecting noise in a fMRI time series is participant motion. What I mean by that is the participant moving their head while they're inside the MRI machine. This video, for example, is just showing a bold data set and playing it over time. So every frame is 1 TR. And you can see that the participant is clearly moving her head quite a bit inside the MRI machine. And see, this leads to two very unwanted consequences. First, if you just think of it in terms of signal to noise ratio, the signal in terms of the amount of the change that mental activity typically induces in bold is somewhere between 0 to 5% if you're really lucky. If you're really hammering visual cortex with something like a flashing checkerboard, maybe you can get a 5% change, but that's the maximum. Usually, we're talking about 0.8 or 2% signal change at most. The order of magnitude of the signal change because of motion can be 100% to 300%. So if you think of it as signal to noise, the magnitude of the noise due to motion is just gigantic compared to the magnitude of the signal due to mental events. So any motion will dwarf the magnitude of our signal and will essentially swamp our signal of interest. The second problem is that we lose the correspondence between a given voxel and a part of the brain. If you look at the video right here, just imagine that where my cursor is, that's one voxel. Now, at the beginning of the sequence, my cursor is almost outside the brain, right here, but during motion, now it's inside the brain. So I'm losing the correspondence of which voxel stands for which part of the brain. Right? You could imagine that if there were a really severe motion, just imagine that we have a voxel right here and in the front of my brain. Just imagine that I moved by 180 degrees. Now that same voxel will be sampling data in the back of my brain, right? And that we can't have. We need to know where a certain voxel is coming from, meaning we need to know that the signal inside a certain voxel is for this area or that area. But it can't move over time, else we lose this correspondence. Let me give you an example of just how bad motion can be in terms of signal to noise. Let me show you just by how much the signal can change because of motion. So this is a slice of a functional image, a T2 star weighted image. And let's just focus on this little piece of the brain down here. In fact, let's focus on the blue piece of the brain, which is zoomed into right here. So see these collars, right? These little voxels from the brain. Well, what I'm writing down here is the value of the bold signal inside those voxels, which is nothing but the number that gives rise to these collars. Okay, so the collars inside each voxel really are just a representation of the value of the bold signal in them. So for example, this voxel here is really bright, so it has a strong bold signal, 507. This one here is really dark, so it has a really low bold signal. When we captured the TE, right, that when we snapped the picture, the strength of M0 was 53 in this box. Whereas in this box, it was 507. Okay. So these are the values of this piece of the brain. Now let's assume that our participant moves their head by one voxel. Now one voxel is typically 3 millimeters. Nothing. It's the smallest motion. So let's assume that this brain moves this way, so towards the bottom right, by one voxel. Nothing, 3 millimeters. It's hard to even monitor not to move your head by 3 millimeters. So essentially what happened is that all the voxels moved one to the right, pretty much. Right? So this voxel here that was 507 has now become 663. It has changed, right, by 1/5 of the signal. It's huge. It's a huge jump. Look at what happened to the voxel down here. It went from 53 to 170. It changed by more than 100%. This voxel that was kind of gray here went from 89 to 507. Multiple times 100-fold change. So the amount of signal change, so suddenly this signal was somewhere around 89, the participant moves by 1 voxel, again, nothing, 1 voxel, and suddenly the signal that was here now jumps by over 100% of the strength of that voxel, of the value of that voxel. The brain is never going to give you such big of a change. So again, if you think of it in terms of signal to noise, the changes due to noise are so huge that it will be impossible for us to see the changes due to actual brain activity. So this is the giant problem with motion correction, with motion, and that's why we have to somehow correct for this motion. Now, how do we do the correction? Well, it's a fairly simple process, and it goes this way. Let's just take the first, so each slice that you see here just represents a whole volume, okay? So this is volume 1, volume 2, volume 3, etc., etc., etc. So what we do is something fairly simple. We take the first volume, we're just going to call that the reference, okay? We're going to put it right here, call that the reference. We could have picked any other volume. I just picked the first one. Different software will pick different volumes for doing this. Then you take the second volume, you put it here. What you do is you subtract the 2 volumes, and you get this kind of difference image. So you get all the parts, all the voxels that are very different between these 2 images. In fact, if you square that, if you square the difference, what you get is this image where everywhere there's a difference between these 2 images, you get some white. The greater the white, the more different these 2 images are, which means they're not aligned. So what you do is you take a reference, you take a second volume, you subtract it from the reference, you take the difference, you square it up, and then you get all this white. What motion correction does is it takes the second volume, this volume right here, and it moves it, right? It rotates it, or translates it up and down, right, left, back and forth, and it moves it trying to minimize the difference between the reference and the volume. So it tries to it moves it so that you get as little white as possible here. And the idea is that the movement that gets as little white as possible means that you successfully took this volume here and managed to align it as closely as possible to the reference volume. And this way, you've taken 2 volumes that were slightly, where one was moved with respect to the other one, and you kind of realign them back so that they overlap as perfectly as possible. And then you take the third volume, you put it here, you subtract it from the reference, you take the difference, square it up, get this image right here, and then you move the third volume as much as you can, right? Either you rotate it, and so there's 3 directions of rotation. You can rotate it side by side, which is called yaw. You can rotate it up and down, which is called pitch, and you can rotate it sort of side to side, which is called roll. So you rotate it, as you can, and you translate it either on the side to side axis, so the x-axis, the back to front axis, the y-axis, or the up to down axis, the z-axis. So you rotate and translate the volume so that it matches as well as possible the reference volume. How do you know when it matches it as well as possible? Because you have as little white as possible. And you do this for every single volume, which means you're essentially you're rotating and translating each volume back to fit as well as possible the same reference volume. This is how we do motion correction. And then you can simply, for every volume, you can actually specify how you translated it and how you rotated it. And now you have a transformation to go from the original data and try to fix it. You essentially, these parameters tell you how you're fixing the data in order to realign it. Now, most imaging software will also show you how much did they have to rotate and translate each volume to fit it to the reference volume. And what you're seeing here is how FSL, the software that we will use, depicts this. So there's time on the x-axis, and this particular graph here is showing the translation. So it's showing by how much millimeters did it have to move in the x direction, y direction, and z direction, each volume to fit it to the reference volume. So for example, the first volume it had to translate it in the y direction. So presumably it had to move it backwards. And then this volume right here, it had to move it a lot up by 4 millimeters. Sorry, it had to move it by 4 millimeters in the z direction, which means it had to move it a little bit up, et cetera, et cetera. So this graph is showing you in terms of translation, by how much did it have to move each volume to fit it into the reference. There's a similar graph which shows you the rotation. So this graph is showing you in radians, by how much did you have to rotate each volume to fit it as well as possible in the reference. And I should say the important thing of this graph is typically twofold. There are two things that I typically look at. I typically look at the scale. So have there been big, did I have to adjust it by much? Was the reference volume here and the volume I collected, was it here? And did I have to move it all, did I have to move it by 2 centimeters? So I want to know by how much did I have to move overall? And I want that to be as little as possible. So that's the first thing I look at, the scale. And then I look at, how big, if there's any particular period of big motion, how big is it? And how many are there of things such as this one right here? See here, something must have happened because suddenly I had to move the brain quite a bit compared to before and after. And FSL also gives you this very handy overall summary showing these lines. And the absolute in particular, the blue one, is showing you overall, so including both translation and rotations, by how many millimeters did I have to move each volume to fit it into the reference. And just like before, I care about the scale. So 0.8 millimeters is all right. It's not bad. And then I just look at whether there's a lot of spikes, meaning are there a lot of instances where the participants suddenly had sort of a big motion or something like that. And I want both to be as few as possible. And here's an example of a data set before motion correction on the top and after motion correction on the bottom. And you will notice that if you focus on the one of the bottom, even if the one on the top is moving a lot, the one on the bottom is doing much better. You will notice that there still is some movement. So we didn't fix it perfectly, but we did a pretty good job. We already mitigated a lot of the motion that was in there.